Okay, so now we're going to look at a new section in this class, or new chapter. We're getting into work and energy and power. So we start off with work, and again, we're going to start at the bottom, work simply, and then build our way up. Now, again, the physics toolbox is going to be really important because we're not going to only deal with things in this chapter, we're dealing with things that in the entire course and outside. We're mainly in the entire course, so the physics toolbox is going to be really important to continue using. But the definition of work is applying a force over a certain distance. It's that simple. So like if you're pushing on a desk that's really heavy and it's not moving, you may sweat a lot, you may grunt a lot, and your feet may slip, but the desk isn't moving, you have done no work. You're better off pushing a pencil that doesn't weigh hardly anything at all. You get more work done with that than you will pushing a desk that won't be pushed. So, when we take force times distance as our equation for work, the label is going to be, well, force is also kilogram meters per second squared. Distance, of course, is meters. Multiply those together, get kilogram meters squared per second squared. However, that's a bit clumsy, so they decided to call it a joule, or joules for plural, named after the English physicist James Joule, who was also, I guess, a master brewer as well, and applied a lot of his science to his brewing company. What we're going to do at this point, because that is a derived SI unit. And I use the word derived, meaning that it's not a fundamental unit. Fundamental units like meters, seconds, grams. Liter is a derived unit. It's actually 1.1 meters quantity cubed. So it's the cubic meter is the SI unit, fundamental unit for volume. Well, actually that's derived because it's based upon the meter. So pretend like I didn't say that. Anyway, there's only like 7 of them. This is a derived unit, which is kilogram meter squared per second squared. There's all kinds of derivations involved with that. All right, so let's take a look at some examples on how we use that. How much work has been done on pushing a 65 kilogram crate 40 meters across a frictionless ice skating rink with a force of 150 newtons? Well, of course, frictionless surfaces, that's a physicist's dream. But we're going to use the formula F. I'm sorry, not F, we're dealing with work now. Work equals force times distance. The amount of force that's applied here is, I already forgot because I made all these mistakes already. The force is applied is 150 newtons, and the distance in which it is pushed is 40 meters. So you just multiply these out, you get 6,000 joules, or Newton meters. Some people will put, but joules is the accepted form of Newton meters. Well, that's a pretty simple problem. I mean, that's just puppy stuff there. Let's do something with a little meat to it, all right? So, let's go on to the next scenario. How much work has been done when pushing a 65 kilogram crate 40 meters across a floor in which the coefficient of friction between the two surfaces is 0.750. So now we're dealing with a mu here, and we have the same scenarios we had before, except for the friction thing here. So let's put that on there. Mu is 0.750. We still have a 60 kilogram crate, and we have a distance of 40 meters that we're going to push it. So this is our distance, this is our mass, we don't have our force, okay? So what we need to do is, since we have mu, we know that mu is defined as the frictional force divided by the normal force. Now the frictional force can also be the forward force, because that's the amount of, if you have yourself going at a constant velocity, and that means the forward force and the backward force have equalized. So the frictional force and the forward force are the same. Okay, so we want to solve this for F sub F. Well, where are we going to get the normal force from? Well, since this is a surface, a flat surface with our 60 kilogram crate sitting on top of it, the normal force is the force of gravity, better known as weight, right down on it. We aren't going to be pulling it or pushing it like we talked about before. That comes later. So FW is 60 kilograms times 9.80 meters per second squared. And that gives us 588 newtons. Okay, so since we know that work is equal to force times distance, then this is going to be 588 newtons. But wait a minute now. No, it's not, because that's just the weight. We want F of F here, not F of W. That's just, we're going to have to figure that out from that. So we go ahead and plug in 588 newtons right there. We multiply, then get F of F by itself. We multiply 0.750 times 588. And we get 441 newtons. So we're going to use that for our forward force. 441 newtons times the distance, which is 40 meters, and we get 17,600 joules as our answer. Okay, all stuff we've had before, but now we got to remember what mu means, and we got to know what weight means, and so a lot of review or a lot of using of the physics toolbox to get through a problem like this. But wait, there's more. Let's take another scenario. Oh, this is going to be so much fun. All right, so, now we have a 25 kilogram crate being pushed with a force of just 10 newtons on a sheet of ice, frictionless surface, for 20 seconds. How much work was done then? So 25 kilograms, 10 newtons, 20 seconds. Okay? Let's see if I actually remember that. So we got 20 kilograms. I've kind of screwed this up already. Oh my goodness, I'm so old. Okay, 25 kilograms is right. 10 newtons and 20 seconds. Oh, okay. I said 20 kilograms. 25 kilograms, 20 seconds, 10 newtons. All right. 20 seconds and 10 newtons. 20 seconds and 10 newtons of force. So that's our force forward. This is our time, of course. And this is the mass. And the question we have here is, what is the amount of work being done by this? Well, force. Work is force times distance. Okay, well, we have the force. That's 10 newtons. Oh, yes. But the distance. Now, how are we going to figure out the distance here? Well, it turns out that we're going to have to get that from the combination of all three of these. Okay, now we know that force equals mass times acceleration, and we know the mass is 25 kilograms. So we can find the acceleration from that, right? So we divide by 25 kilograms, and we get A is equal to 10 newtons divided by 25 kilograms is 0.400 meters per second squared. Well, that doesn't exactly give us the distance yet, but there's always that big but. We can find the distance by using, this is an accelerating object, so we use the distance formula using accelerating object starting at rest, and we push it forward. So this becomes 1/2 AT squared. So 1/2 or 0.5 times 0.4 meters per second squared times the time squared, 20 seconds, quantity squared, and that distance then is going to be 80 meters. So I plug that in right here. 10 newtons times 80 meters is 800 joules. And that, ladies and germs, is how we do these work problems. All right, practice problems. Let's take a look at those real quick here. We have 4 of them. How much work, blah, 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 blah. And we end up with how much work, blah, 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 blah. It almost sounds like the same problem, but they're not. So take a look at your script or take a look at the video real close, or just pause it so you can see what we got here. I can do that all day long, it's fun. Anyway, good luck.